Okay, thank you and good morning, and thank you for joining me for this presentation about I/O checker, verifying your FPGA is correctly on the board. So I have prepared a number of slides, and first we're going to step into what we call the problem description. What are you faced with when you are placing a large FPGA on the board? What do we do with I/O checker? What does it check for you? And we started out as a kind of design tool, a verification tool, but we're also moving towards design, and we wrap up this presentation with the conclusions. When there is enough time left, I will also do a quick demonstration about how the tool works, because we always present it as a very easy to work with tool, but nobody really believes that until they've seen it themselves. So if you're putting a larger FPGA on the board, the biggest problem you always have, there is so many requirements and restrictions. So you have power and ground. If you have a larger FPGA, you can have up to 10 different voltages being used, different pins, different voltages. User I/O, an FPGA is really flexible, but some problems are just either very hard to find, take you a lot of time to find, and problems in power banks, they can be disastrous, requiring you to do a respin of a board. And with the user I/O, you have all kinds of combinations. You have the LVDS pairs, and it's just a lot of work manually verifying that it's done correctly. And what I often see is that people do that initial check at least once, so they're trying to run through all the schematics, getting a net list out of it, comparing it with the pin list, but that's only a one-time action, because it just takes a number of days to do it really correctly, and then if changes are being made either on the PCB side or on the FPGA side, they more or less hope and assume they've done it correctly on both sides. So what do we see with FPGAs? Because they are so large that there are different people involved in doing the FPGA. So you have often VHDL engineers or Verilog engineers doing the FPGA part. PCB is done by somebody else or multiple people, especially with FPGAs. When they are really large, you see a real design team working on the FPGA. And there are very different ways of working. So when the FPGAs are large and the board is even larger, then I often see that even work on the PCB is started before the FPGA is being implemented. Sometimes engineers make a kind of zero design to have an initial placement, but then the board starts while the FPGA has not been done yet. Then the second difference is, do you work with generic symbols, so symbols being generated or being present in the PCB tool, in this case in Altium, or are you working with application-specific symbols to try and reduce the complexity of the symbol, because you already see with the very large FPGAs that are currently broken up into about 30 different symbols for one FPGA. And although the FPGAs are very flexible, the pin assignment has a large impact on the PCB performance. So if you're able to do some swapping, you could have a board which is better to route and easier with a higher frequency performance. So if you don't use any tooling, what do you need to do? You need to extract the netlist from the schematic. So that's quite often not that difficult, but then you have to limit it yourself to the FPGA. So there's one or more FPGAs in the design. You need to extract the information for one FPGA. You probably have to sort that, and then you have to compare that with the information being generated by the FPGA tool. And unfortunately, different vendors have different formats, and everyone has its own way of putting information in the file and also presenting you with different information. Or they've put it in different files, which even makes more work of getting all the information you need to have. What we see when the designs get larger, that it's really time-consuming to verify your FPGA. And because it's dull work, you have to walk through a list of 1,000, 1,500 pins. It's also error-prone. In the beginning, you're awake, but when you are halfway, it's getting difficult. And some errors like swapping signals with one index is 12 and the other one is 21, is easily made. And if you do it by hand, almost no one really does a second verification if any design changes have been made, and they all assume they've done it correctly. What kind of problems do we see in the verification? Managers often tell me that people are using the same name in the FPGA environment and in the PCB. Reality turns out it's different. There are always differences in names, either because your schematic capture system has some limitations on the names they would like to use, or there are company rules about how the VHDL names are being used in the FPGA. So there are differences. Also in one package you would be using underscores or smaller than or brackets for arrays. In the other one it's without. LVDS signals like underscore n, underscore p, sometimes the underscore p is not present, differences. When you're looking at power, all engineers have some way of really defining their power. Yep, this is typically one I often see, P3, V3, meaning a positive 3.3 volt. But there are different ways of doing that, and then sometimes you can just see in your pin file, if you have the information, 3.0. Or even if it's worse, it can be any, or it can say 1.2/1.5/1.8, so multiple values being allowed. In the PCB, you often have, for the power circuits, we have decoupling circuits. Then the voltage has been derived using an inductor and capacitor for certain specific power requirements. We have pull-up circuits, we have pull-down circuits. And what I sometimes call, I always say, it's not rocket science what we do, but it's a kind of needle haystack problem. You have 1,500 pins, and you have a few potential problems. And the question is, how do you get those few potential problems into your focus area? So, for that, we have I/O checker. What does it do? It verifies between the FPGA information and the PCB connectivity. Mostly, we start with the schematic part. And because we often see that there are slight differences between the two environments, we have something we call fuzzy matching. And the next step, besides fuzzy matching, is rule-based matching. The rule-based matching is something we developed to help you automatically match large groups of pins which look the same or have some kind of relation between each other, but which are not exactly the same name. Then we have another group of matching, which is power and ground matching. For power, you don't really matter what the name of the signal is, as long as it's the correct voltage. That's the only thing which is required for correct operations. But every VCC I/O bank can be on its own different voltage. The LVDS pairs, they do not swap any P and N versions because you will end up with a problem. So what we call also an I/O checker, it's a smart way on the to concentrate on differences, because we have a lot of different ways of presenting the information to you. And then reporting. So something simple as out-of-date files. It happened a few times to us that we got information from a customer and they changed the constraints, but they just forgot to run FPGA synthesis again. So the tool also reports simple things like, you've changed your constraint file, but the constraint file is much newer than the pin file from the FPGA tool, probably indicating somebody has forgotten something. And once a project has been defined, it is also very easy to see changes in the design. So if any changes have been made in the design, voltage changes, locations, I/O types, we report all those changes when you reprocess the information. So I always do it graphically about what's I/O checker. I/O checker is a kind of spin in the middle between the different environments. In the FPGA side, you have many different ways of working. You can have a specification based on comma-separated values. You can have VHDL there. You can have your constraints probably. You have a pin list, some kind of format. And we always prefer to work with the pin list because that has most information in it. We read that in, and then we also read the information based on the netlist from Altium Designer, and we start comparing that in an intelligent way. Well, we also have an internal database of all the available FPGAs in our tool, so we know what to expect and we know which pin should be a power, what should be a ground, and that helps you also organize the views in the end. And if you work that way, then the last thing is view and organizing the problems. We normally put problems on top of your list, and then it's quite easy to see what the result is. And from it all, we have a kind of HTML report, which tells you, which hopefully should tell you that you have no errors left and everything is correctly being connected. So matching, well, and I will get to an example later on in the presentation, but if you read any information, there are a number of things quite obvious. Signals which have the same name on both sides in the environment, something you really don't have to look at, they're correctly connected. Then we have the fuzzy matches, so, and that's being used like using bus indexes or flat names, having underscores in signals. You can turn it all on and then we try to automatically match that as well. The next step, family and power matches like pins which are called not connected or do not use. We know you shouldn't use them, and if they're not connected on the PCB, they're also validated automatically. For powers, if you recognize the voltage and the voltage is the same as being specified in the pin file from the vendor, you're also good. Next step, the almost last step, the rule matching. We try to find automatically, because it's quite difficult in the beginning for engineers to use it. Using regular expressions, we find common ground, common sense between signals which are slightly different in the FPGA environment and in the PCB environment, but which are probably intended to match. And if we find a number of those potential matches, we will present that rule to you in the tool during the verification. And once you accept it, that's something you don't have to look at it anymore because it's validated. There are always signals left, unfortunately, which we cannot do automatically and which you should, by hand, more or less accept, say, well, I verified this signal, it's okay, and I don't have to look at it anymore. And the same holds sometimes for power mismatches. It can happen like signals like the battery signal, the power battery in a lot of tools like with Altera. They say it's 2.5 volt, but it's also allowed to connect it to ground. Or if you would have certain power groups, that it's sometimes possible to connect them to a different value, says the documentation, than being described in the pin file. But we have the philosophy, what's in the pin file is the rule for us, so we use that information. So it's sometimes possible that there is a difference between that and how you connected it, and then you can manually validate that difference. So the fuzzy matching, what I mentioned, quite often, how do you indicate a bus? Everyone has a different system, underscored characters. So here I have a number of ways of writing down the data address 15, which for us, if you enable the fuzzy matching, is all the same. And it already gives you a number of hits when doing verification. Power matching. So you have the ground pins, the real ground pins. You have the power pins when the voltage is recognized, and we normally are able to recognize the voltage levels being specified in the PCB. Compare that to the information, if the information is present in the pin file. And there we also see different quality of results, because we noticed that, or we know that both Altera and Xilinx deliver the best information for the designer. They're the most complete within Lattice, and Microsemi, it's a little bit worse because they do not specify the power voltages for pins in their report file. And then, of course, you have sometimes pins which are not being used and which could be connected to ground, like Altera has G&D Plus or G&D Star as being a way of indicating that user I/O pins which are not used can be connected to ground. So then the most difficult part of our tool, the rule engine. The rule engine helps you to validate groups of signals which are correctly connected but which still have different names in your environment. And that's being used on regular expressions. And one of the examples here is I have a databus underscore PCI with a number in in VHDL or in my pin file, and it has been named data_PCI12 in the PCB environment. And by defining a rule, you could automatically match a large array of signals this way. And the rule engine has the capability of aligning, even not aligning non-straight signals. So if you have something which would have an offset of 16 characters, you could match that. Or typically in VHDL, you're capable of defining ranges which are up to or down to. So if you would have an inverted array, you could also automatically match that. And as we know that it is quite difficult for engineers in the beginning to define those kind of rules, we have a rule generator in the tool which helps you automatically tries to find these kind of rules, and that presents to you as a potential solution. And that way validating a number of signals. I always say this is also the most dangerous part of the rule generator, because it will come up with proposals which might not always be the right solution. I've seen an example where somebody switched to 16-bit arrays exactly and really did a well job. So then the rule generator we have will come up with a solution saying, well, if you switch these signals, you would have 32 matches. But if you need to verify very carefully that it's indeed your design intent. And in the last step, we always have a number of signals, either because we don't know at the moment, like the control signals for your FPGA, or you have, in this case I don't have an example of that, you have a signal name which does not relate at all to the signal name in the PCB, that you have to manually say, well, I've checked it, like in this case here at the bottom we are having here, it's either user, for instance, as a user I have knowledge that this signal is not being connected, or I have a number of control signals which I've manually verified to be correctly. And in the beginning, in the first top view, I have a number of red dots, and it's all in red, meaning that there are potential problems here, and once they've been verified by the user, then the arrow dots have disappeared and everything became green or black. So, because in FPGAs you have a lot of pins, you have a lot of information, and depending on what you're doing at the moment, you need to have capabilities of focusing and concentrating on your potential problems. So, the first thing we have here is how do you want to look at the amount of signals you have. So we have here the pin view order. You could look at every signal in the view using the pin name, but quite often that's not really what you would like to do. So the standard sorting order we use is severity, meaning all your potential problems are on top of a list. So if you have 1,000 signals, the ones which might be a problem will be presented on top. And then because severity, the problem can be more, then we have the second verification order, which is, for instance, the signal, if it's coming from the pin file, the constraint file. And this already shows you, again, a number of potential sources on which you can use to sort. And then we also have filters of what would I like to see, or what would I like to hide. So if I'm not interested or I'm using only with a constraint file, then I could leave out and not look at all the pins which cannot be defined in the constraint file. And that way I can reduce the amount of visible information on my screen. And now you all think, oh, I've seen a lot of things. Well, this is a kind of screenshot. Initially sorted this way just by pin number, and then we already see a few potential problems here being mentioned, like I have a signal here which is, according to the pin file, 3.3 volt, but it has been connected to P1V2, for which we have derived it's a 1.2 volt. So you have a red error and a dot here, and I also have one signal here on this list which also presents probably a problem because it's in the pin file and in the constraint file, but it's connected to ground on the board. But now I have a view for which it's organized by pin number, and if I go to the next slide, I would here have a view being organized by severity, and I have all my potential problems on top. So I can directly see the worst ones. What we call the worst ones are the power mismatches. And we see a number of signals which should all be 3.3 volt. different information although, but some of them or all of them are connected to 1.2 volt. And then we also see something special here, like I have a signal on the PCB being called VCC PLL out, which is indicated here by this symbol, connected with a decoupling circuit to my main power rail, which is 1.2 volt. So we know, although there is not really a voltage name here in this derived name, it is being connected to the main power rail of 1.2 volt, and that still does not fit the 3.3 volt specified by the FPGA tool. So my power errors are here on top, and then I have a number of user I/O signals, and for which I have a problem, and it's quite easily here to see that somebody swapped 12 and 21. And I also have a number of signals, like here I have an example which is not being verified by hand, but if you have an intermediate signal like $21.34, it's just impossible to match that, and that's something you need to verify by hand. But here, some errors, and here is the other signal, the RDN2A, which has been mismatched because I have a signal here, that same signal, which is connected, not being used on the FPGA, but it's a user I/O signal on the board. So now I have, from my 672 pins, it's quite easily, I only have to focus at 12 potential problems. And they are problems, and you need to fix them. These problems here, the user I/O problems, can be fixed in two different ways. You could either go to the PCB tool, change that. You could also make changes here to the signal constraints and change it in the FPGA tool. The power problems, however, always need to be fixed on the PCB. In this case, I had a number of problems being presented, and if you want to fix them on the FPGA side, we can have a constraint generator who can adjust the constraints which are present in your project, and it can make a number of proposals here, and if you accept those proposals, you would see them appear here and with using a new color, and I could update my FPGA constraint file based on the changed information in I/O checker. So this is an adjustment, a change. Might you have started with your PCB first or the schematic? Then we could also read in that information and use it to generate constraints from the PCB information. So we are able to update or to generate a new constraint file or to update an existing constraint file, keeping the constraint file, the order of the constraint file and all the comments intact, and only making minor changes to those signals which have a different location assignment or a different I/O standard. One of the nicest things is once you've defined a project in I/O checker is that you can do a re-verification in just a few seconds. Once we know what the sources are, you can reprocess all those files in seconds, and if any file has been modified since the last time we processed that file, it's even pre-checked, so you can just hit the OK button and it will start reprocessing all your data files and also telling you what has changed in I/O standards, in location standards, and power properties, other connectivity in the net lists. Because when you're doing it again, you would like to know what has changed. So that is really a re-verification once a project has been defined once is really a work of seconds. If you started with the FPGA design, well, let's put it differently. We initially started as a verification tool. Really just picking up netlist and having the FPGA information and comparing them in an intelligent way. We're now moving more to the design part. If you started with the FPGA design, we can use that information to automatically add wires and ports to symbols of the FPGA you have instantiated in the schematic, making it more easy to make sure that the same signal names or almost the same signal names are being used in the FPGA tool as being on the schematic design. And if you've started with the schematic capture and started over there, we would be able to generate the FPGA constraints from that information or create a VHDL or Verilog top-level unit based on what's in the schematic. How does that look? If you would like to update a schematic, then where do you want to start? Do you have constraints? Do you have a pin file? Perhaps you only have a specification in a comma-separated values file. You can read it in. You can decide what you would like to use. You tell us what your Altium project is, what's the reference designator, and how if you would like to add I/O ports. Some other options like do you like to automatically add wires for power ports, or would you like to ignore them? And if the design already has been connected somehow, if you have updates, would you like to replace or update those signals? So there are the things you can do in the user interface. We have also some file configuration options like the wire length, how long should the wire stub be, which we automatically add. Would you like to have LVDF's diff pair parameters being added to the wires in the schematic? And then you just press the OK button, and we start up Altium Designer with a specific command line to iterate through all the different schematic pages, and everywhere we find your FPGA, then we start adding wires to it. This is a kind of example which I made just more or less showing the different things. Normally people would not put power and ground and user I/O banks in just one schematic. I've done that in this example just to show you what's being generated. So I have all the ground signals here being automatically added, a number of powers. I have a number of user I/Os which have been connected, and on this device also there are a number of do not use or not connected pins present, which also have a message, an ERC, do not check symbol being attached to it. In this option I selected to use ports, so I have a number of ports being present here. I have some voltage terminals there, and I could easily use that to create a top-level symbol of this information. And you have it correct by construction. And if you started the other way around, if you started with a schematic, then you could use that information to either generate, to generate constraints. And there are different ways of generating constraints and how you want to work with it, and if you want to have LVDS names and so on. Can be using a dialog, doing all at once. It can also be individual, using drag and drop. Like if you come by, I could show you. Export information to comma-separated files, create top-level units. We try to make it as easy as possible for you when doing the verification and the design part. Some other features, like I've said, most companies do have some kind of specification somewhere which is either in Excel or another format, which always is capable of generating comma-separated value formats. We could import and use that. One of the other nice things is we have what we call a device view. Normally what we see is the FPGA designer is very happy having a list of signals. But when people are more used to working with the PCB or the schematic capture, they also would like to have a kind of view of how the device, the footprint of the device looks like. And we're also capable of showing what we call the alternate symbol. Suppose you have an FPGA for which you're not sure if you have enough logic in the package you selected and you want to be able to move over to a larger device in the same package. Then you could say you want to have an alternate device. And here in this section we are showing you what is different. So in your selected device you have a number of ports which are unconnected. But might you move to a larger device in the same package, then it will become regular user I/O. Or even in the past, Altera had a lot of FPGAs in the Cyclone 3 and 4 arena where user I/O could become a ground or could become a power depending on the migration path you selected. And all the symbols, we tried to look for a number of symbols which denote the kind of functionality present, like I have ground pins, I have analog power, I have LVDS pairs, of LVDS capable pairs, I have a clock capable port pin there. So we try to present as much information as possible to you. Didn't have an example, but the rule generator is really even a necessity. I think it will help you quickly concentrate and help you generate and give you a start on the rules. Doing that. Then additional netlist information. A lot of signals can have pull-up and pull-down resistors, and sometimes it's interesting to know which signals are being connected to ground. So here I have an example of a signal which is directly connected to ground using a resistor. Or here I have a pull-up signal, and we present you which pull-up voltage belongs to the circuit. Decoupling circuits, as I also mentioned before. Dangling wires, something that should not happen, but unfortunately we've received enough designs from customers where they had still parts of the design not being connected. The NC connected, and also there are also companies which use a signal name, for instance NC as a signal, as a wire name being present in the schematic, but which does not really exist on the final PCB, meaning it's not connected. So we're able to handle that as well, to present you as much information as possible. And besides that, we also have a command line version using a tickle interface, which helps you to automate things. Suppose you would have the nightly builds or things being run, then you could use the tickle interface to set up projects and to automatically run verification and present results at the end of the day. FPGA support, well, we more or less we have everything which is current and which is new. For Altera, the only device we do not have yet, because it's not made publicly, is the Stratix 10, but everything else is present in IO Checker. All the lattice devices, micro semi devices, and for Xilinx we have everything which comes up, and which is also for us, it's a large part in the software tooling, which you as a designer does not see, but we try and we automatically mine the databases of all those vendors to get the information out of the FPGA vendor and into our own tool, because we think we should automate this as much as possible to make sure that there are no mistakes, because any handwork everywhere in the design could potentially result in errors. So we have a large system at home trying to get all the information from all the FPGA vendors and putting that into our own internal database. What we like to do in the future is, until now we've seen we are able to wire the symbols of the FPGA, but what we like to do in the future is to automatically generate symbols, or to have a kind of large symbol which would break down into different sheets, adding and connecting to the different elements of your FPGA, making it easier and to reduce the amount of work you now have to do by hand. Well, you could also think about, and I think that's something possible already in Altium Designer, but optimize assignments based on the physical board layout and the connectivity, but also keeping in mind which kind of signals you are using, what the I/O types on those signals are, because there are quite some restrictions on what you can do. The multiple FPGAs, of course, at the moment we can handle one FPGA on the board. So if you have more than one FPGA on the board, you could define multiple projects, but I also have some customers asking to have that in one single project. And the last step is for us to tighten integration between Altium Designer and IO Checker. Currently we do most verification based on a netlist we extract from Altium Designer, but we know we'd like to make it easier even for you and just extract the information from the PCB project without you needing to really specify or generate a netlist. For us, we think that IO Checker fits on all the flows, independent on where you start and how you work. And something you need to to verify for yourself, but it's really easy to use. And it needs to be easy to use because most FPGA engineers only verify an FPGA once, twice a year, and then they will be on the next project. So with this kind of software, it needs to be very easy to use, and you need to understand what the software does in order to have trust in the results. And especially the re-verification is also important because now, when you do it by hand, almost nobody really re-verifies every change they made. And in the end, it can save you a lot of time, and in case you have a burning board, it can save a lot of money. I think I'm at my last slide. Do you have any questions at the moment for me? Yes, I think I have a microphone here. Yeah? Did you press the button? Because otherwise it's off.
Hello, yep,
yes, you're working.
Sound code. So forgive the slightly dumb question, but having used the internal tool within Altium Designer anyway, not for doing the actual FPGA design, but doing the design synchronization, what's the? I'm not seeing a huge. Maybe I'm missing something, but I'm not seeing a big difference between the existing Altium support for FPGA and your tool. Okay, well, I don't exactly know because I never looked at what exactly Altium has done in the past. Because we found in the Netherlands, which is my home base, that although Altium presents that solution, we did not run into any customers using it. And I think what's quite different is we have what we call the rule engine, which helps you verify between different environments which do not exactly have the same signals. And not sure, but I don't think that's present in the Altium solution. And we also verify the power signals, so we really know how to recognize the voltage values from the schematic and compare them with the voltage information that's being presented by the FPGA vendor. Okay, so I mean, I can't speak for the voltages, but what I can tell you is one of the easy ways you can go from a schematic is you can just simply tell Altium to create you a top-level HDL in Verilog or VHDL, and that's it. It's straight mapped. Yeah, I know you could use it, but quite often I see different worlds using different signals, sure. And then they need the verification. Okay, thank you. Yep.
Any other questions?
Any other questions? You have a question for me. Just one question from my side. How many of you are using FPGAs? Okay. Thank you. Where are we with the time at the moment then? You know?
I think we're probably right there, about 4 minutes.
Okay. Well, 4 minutes is quite short. So if you would like to see I/O Checker in action, it's fast to use, it's easy to use, but I'm down here in the expo, and I can give you a really fast demonstration about the possibilities or other questions you might have, and I'll be happy to answer them. Yeah?
Great, thank you.
Okay, thank you.